And for the next, we have the integral of a non-negative function, which is defined as follows. If f is a non-negative measurable function defined on a measurable set E, we define integral of f to be supremum of integral of h, where supremum is taken over all h which is less than or equal to f, where h is a bounded measurable function along with the property that measure of set of all x such that h of x not equal to 0 is finite. So this is the definition of an integral of a non-negative function, and we have a proposition which is related to that. If f and g are non-negative measurable function, we have these three statements. Integral of cf over e is same as c into integral of f over e, where c is a positive real number. And the next, integral of f plus g over e is same as integral of f over e plus integral of g over e. And finally, if f is less than or equal to g almost everywhere, then integral of f is less than or equal to integral of g over e. Let me look at the proof, and again the proof of 1 and 3 are simple and it is left to you, and I am going to prove the second one. Well, to prove this, I will consider two functions, say h of x to be less than or equal to f of x, and another function, say k of x, which is less than or equal to g of x. And so I have h of x plus k of x to be also less than or equal to f of x plus g of x. Thus, I have integral of h over e plus integral of k over e to be less than or equal to integral of f plus g over e. Now taking supremum, I do have integral of f over e plus integral of g over e to be less than or equal to integral of f plus g over e. Now this proves one side of the inequality, and I call that as 1. It remains to prove the other side in order to get the equality. Now I will consider a function, say L, which is a bounded measurable function, and that vanishes outside a set of finite measure, and I take L of x to be less than or equal to f of x plus g of x. So L is bounded by f plus g, and thus I will define a function h by setting h of x to be minimum of f of x and L of x, and I define k to be the function L of x minus h of x. Again, remember that h and k are bounded by the bounds of L, and h and k vanishes where L also vanishes, and thus I have integral of L over e to be same as integral of h plus k over e, again which is same as integral of h over e plus integral of k over e, and this is less than or equal to integral of f plus integral of g over e. Since L is less than or equal to f of x plus g of x, integral of f plus g over e is less than or equal to integral of f plus integral of g over e. If I call this to be 2, 1 and 2 implies the equality, which will complete the proof. Next, we have Fatou's lemma. It states as follows: if fn is a sequence of non-negative measurable functions and fn of x converges to f of x almost everywhere on a measurable set E, then integral of f is less than or equal to limit inferior of integral of fn. And coming to the proof, given that fn of x converges to f of x almost everywhere, and known the fact that integrals over a set of measure 0 is also 0, without loss of generality, I can assume that the convergence is everywhere. And assuming the convergence is everywhere, I will consider a bounded measurable function, say h of x, which is less than or equal to f of x and vanishes outside a set, say E dash, of finite measure. Having this, I will construct a function hn of x by defining it to be minimum of h of x and fn of x. So again, having this to be hn of x, Hn of x is bounded by the bound of h of x, and Hn of x also converges to h of x for each x in E dash. Having Hn of x to converge to h of x for each x in E dash, by bounded convergence theorem, I can have integral of h over e to be integral of h over e prime, which is same as, and this is equal to limit of integral of hn, which is less than or equal to limit inferior of integral of fn over e. So now we have integral of h, which is same as integral of h over e dash, and this is by bounded convergence theorem, limit of integral of hn, and that is less than or equal to limit inferior of integral of fn. Now taking supremum over h, I can have integral of f over e to be less than or equal to limit inferior of integral of fn. So this completes the proof of Fatou's lemma, and you should observe that it is less than or equal to, but we can also have strict inequality in Fatou's lemma, and that's most important, and let me see the example for it. Next, to see that we may have strict inequality in Fatou's lemma, we will consider an example by constructing a function fn from R to R and defining it by fn of x to be 1 if x lies between n and n plus 1, and it is 0 otherwise. Clearly you can see that fn is a simple function, and also we have fn of x to be greater than or equal to 0 for all x, and each fn is measurable. Each fn is measurable, and having the nature of the sequence defined, we can have f1 of 1 to be 1 and f2 of 1 and all the other things are 0 and so on. So this implies that limit of fn of x to be same as f of x, which is nothing but 0, and observe that this is a pointwise convergence, so we have integral of f to be 0 over R. And now coming to fn, since fn as said is a simple function, I can express fn as a linear combination of characteristic function, so which is nothing but 1 into chi of over the set which is defined n plus 1. So seeing the integral of fn, this is nothing but 1 into measure of the set n plus 1, which is nothing but 1. So integral of fn over R is 1, whereas integral of f over R is 0. Therefore we have here integral of f over R to be strictly less than limit inferior of integral of fn, where this is 0 and this is 1. So one can have strict inequality in Fatou's lemma. In the previous Fatou's lemma, we had inequality. If you question when will be the equality, monotone convergence theorem gives you the answer, and the condition should be it should be an increasing sequence of non-negative measurable functions, where in the previous case it was just a sequence of measurable functions, and monotone convergence theorem states that fn be an increasing sequence of non-negative measurable functions, and same as the previous Fatou's lemma, fn converges to f almost everywhere, then we have integral of f to be same as limit of integral of fn. And coming to the proof, it's again quite simple. By Fatou's lemma, we directly have integral of f to be less than or equal to limit inferior of integral of fn. But given the statement of the theorem, we have fn to be less than or equal to f for all n. since fn is less than or equal to f for every n, we have integral of fn to be less than or equal to integral of f. So, but this implies limit superior of integral of fn is less than or equal to limit of integral of f. But still this implies limit superior of integral of fn is less than or equal to, we can still have this to be less than or equal to integral of f. So if I call this to be as 1 and if I call this as 2, by inequalities 1 and 2, I can have the equality limit integral of fn to be same as integral of f. But one should remember that monotone convergence theorem need not holds good for a decreasing sequence of non-negative measurable functions. So it is left to you to find a suitable example to show that monotone convergence theorem need not holds good for a decreasing sequence of non-negative measurable functions. Next we have a corollary and a proposition to see, and corollary states that let un be a sequence of non-negative measurable functions, and if f is equal to summation of un n from 1 to infinity, then we have integral of f to be same as summation of integral of un. And we have a similar proposition to that, let f be a non-negative function and ei be a disjoint sequence of measurable sets, and if e is union of ei's, then we have also integral of f to be same as summation of integrals of fn's and n running from 1 to infinity. Next we have a definition. A non-negative measurable function f is called integrable over the measurable set e if integral of f over e is finite. So let me come again. A non-negative measurable function f is called integrable over the measurable set e if integral of f over e is finite. If you like to see an example, if I have a function f from say 0 2 to r, which is defined by f of x to be 1 if x is in closed 0 1 and 2 if x is in open 1 closed 2. Again, clearly you can see that it's a simple function. So as a simple function can be expressed as a linear combination of its characteristic functions, I can have f to be equal to 1 into characteristic function of 0 1 plus 2 into characteristic function of 1 2. So I have integral of f over 0 2 to be 1 into measure of 0 1 plus 2 into measure of 1 2, which is nothing but 1 into 1 plus 2 into 1, which is 3. Since this is finite, I have integral of f over 0 2 to be finite, which implies f is integrable over 0 2. Proposition, let f and g be two non-negative measurable functions. If f is integrable over e and still g of x is less than f of x on e, then that implies g is also integrable. And the proof is just one line proof, because since integral of f over e can be expressed as integral of f minus g over e plus integral of g over e. Since given that f is integrable over e, this should be finite. So if the things at the left hand side should be finite, right hand side should also be finite since they are equal. So if right hand side is finite, we should have integral of g over e to be finite, which implies g is also integrable. Theorem, let f be a non-negative function which is integrable over a measurable set e, then given epsilon positive, there is a delta positive such that for every measurable set a of e with measure of a to be less than delta, we have integral of f over e to be less than epsilon, And heading to the proof, we have two cases here. One is the bounded case and the unbounded case. And coming to the case 1, if f is bounded, say f to be bounded by m, then given f to be non-negative, we can have 0 less than or equal to f of x less than or equal to m. Next, continuing that with given epsilon positive and choosing epsilon to be, delta to be epsilon by m, along with measure of the set A to be less than delta, we have integral of f over A, which is less than, since f is bounded by m, integral of m over A. And by the definition of Lebec integral, this is nothing but m into measure of A. And since measure of A is less than delta, this is m into delta. We have chosen delta to be epsilon by m. So this is m into epsilon by m, which is epsilon. So we arrived at integral of f over A to be epsilon. So this completes the case 1 of bounded, and let me see the case 2, which f is unbounded. Next, for the case 2, which is the case where f is unbounded, we define for each positive n fn of x by, it is to be f of x if f of x is less than or equal to n, and it to be n if f of x is greater than n. Clearly, by the definition of fn, we have fn of x to be greater than or equal to 0 for every n and for each x in E. Since fn of x is greater than or equal to 0 for every n and for all x in E, we also have fn to be monotonically increasing, non-negative, measurable function which converges to f of x for each x in E. Since we have fn to be a monotonically increasing, non-negative, measurable functions, sequence of measurable functions, and along with fn of x converging to f of x for each x in E, we have all the conditions to apply monotone convergence theorem. So by monotone convergence theorem, we have limit of integral of fn over E to be same as integral of f over E. So applying the monotone convergence theorem, we have this equality, and there exists an integer n such that given epsilon positive, we have mod of integral of fn over E minus integral of f over E to be epsilon less than epsilon by 2 for each n greater than or equal to n. So again, this is same as mod of integral of f over E minus integral of fn to be less than epsilon by 2 for each n greater than or equal to n. And again, this is same as integral of f minus fn over E to be less than epsilon by 2 for each n greater than or equal to n. This is nothing but mod of f integral of f minus fn over E is less than epsilon by 2. And now choosing delta to be epsilon by 2n, where A is a subset of E with the measure of A to be less than delta, I have integral of f over A to be f minus fn over A plus integral of fn. I can have this, and since A is a subset of E, this is less than or equal to integral of f minus fn over E plus integral of fn over A. Since we have this to be less than epsilon by 2, this is less than epsilon by 2, and by definition, this is n into measure of a. And since measure of a is less than delta, and we have chosen delta to be epsilon by 2n, we have this to be less than epsilon by 2, which is epsilon. So we arrived at integral of a to be less than epsilon, which proves the condition of where f is unbounded. We have a general Lebec integral, and we have two definitions here. One is the positive part of a function and negative part of a function. Let me see one by one. And by the definition of a positive part of a function f, we mean the function f plus defined by f plus to be the maximum of f of x and 0. And similarly, by negative part of a function, we mean the function f minus defined by f minus to be maximum of minus f of x and 0. So these are the two definitions in general Lebesgue integral, which are positive part of a function f and a negative part of a function f. And we have some three remarks regarding those. If f is measurable, then so are f plus and f minus. So if we have f to be a measurable function, so we have positive part and negative part to be also measurable. And if f plus and f minus are if f plus and f minus are non-negative measurable functions. So positive part and negative part of functions are non-negative measurable functions. And finally we have f to be positive part of a function minus negative part of a function. If we take mod of f, we have it to be positive part of a function plus negative part of a function. And we have one final definition. A measurable function f is said to be integrable over e if both positive part and negative part are integrable over e. In this case, we define integral of f over e to be integral of positive part over e minus integral of negative part over e. So one final theorem of second unit, namely Lebec convergence theorem statement. Let G be integrable over a measurable set E, and let Fn be a sequence of measurable functions defined on E such that mod of Fn is less than or equal to G on E, and for almost all x in E we have Fn of x converging to f of x. Then we have limit of integral Fn to be same as integral of f over E. Coming to the proof, if we consider a function g minus fn, clearly this is a non-negative measurable function which also converges to g minus f almost everywhere on E. So g minus fn is converging to g minus f almost everywhere on E, and so by Fatou's lemma we have integral of g minus f over E to be less than or equal to limit inferior of integral of g minus fn over E. Also, given that fn is bounded by g, and since g is integrable over E, we have f also to be integrable over E, and thus we have integral of g minus f over E to be equal to integral of g minus integral of f over E. But this is less than or equal to integral of g over E minus limit supremum of integral of fn over E. So we have integral of g minus f to be less than or equal to integral of g minus limit supremum of integral of fn. But this implies limit supremum of fn to be less than or equal to integral of f over E. So call this to be equation 1. What we have got is limit superior of fn to be less than or equal to integral of f. So we got this equation by taking at the start g minus fn as a function which is a non-negative measurable function. So in the similar fashion, if we consider a function g plus fn we will arrive at integral of f over e to be less than or equal to limit inferior of integral of fn. So if you call this to be equation inequality 2, so inequality 1 and inequality 2 together implies the equality limit of integral of fn over e to be same as integral of f over e. So this completes the proof of Lebec convergence theorem, and this ends also unit 2, and at the end in the notes you have some handful of problems as exercise. So I'll try to solve it, and which will be useful for 2 marks, and we will continue with unit 3.